Time once again for the WMBriggs show. We have a lot to do today. In fact, we won't finish. In fact, we could never finish. We have to count all the different kind of multiverses they are. And then we have to count all the different kinds of infinity. And it turns out there's an infinite number of them. So we have a lot of work ahead of us. So let's stick around and see how much we can get done. The music that you heard there, I stole from the very first Cosmos show with Carl Sagan from back in 1980, I think it was. Here are the opening words from that show. This is the very first show, and here's what Carl had to say.
The cosmos is all that is, or ever was, or ever will be. Our contemplations of the cosmos stir us. There's a tingling in the spine, a catch in the voice, a faint sensation as if a distant memory of falling from a great height. We know we are approaching the grandest of mysteries.
Well, this was hugely influential, this original show back in 1980, Cosmos. I was a teenager in high school at the time and thought Carl Sagan was a genius. He was an excellent performer. His tone and demeanor and everything else matched perfectly what he wanted to do for that show. Unfortunately, he was wrong about a lot of things. Even his opening statement was wrong about the cosmos being all there is and all there will be and all there ever will be is not quite right. And even physicists nowadays don't believe him. And so we have to figure this thing out. But before that, you heard that music. I think that was those sorts of music were also huge among the geeks and the nerds, of which at that time I numbered myself and probably still am. People used to listen to Vangelis, for instance, and get an album or a tape and listen to this stuff. And not only that, people used to buy these video cassettes of computer animation, and they had these really crude, not quite stick figures, but people shapes were going through various landscapes of diamonds and tetrahedrons and various colors and all this kind of stuff. This kind of stuff was really big. Back then, science seemed to have a direction, and of course, we now know that isn't so much the case with the government intrusion into science. But, however, that's not our subject today. Our subject today is the cosmos or the universe. Now, we need to be very careful about this. What we're going to do is try to think about all the different kinds of universes that are claimed that might exist. And then we have to think about what it means to exist as opposed to what we know about what exists and what is actual and what is only potentially actual. And then we're going to marry this all back to my favorite subject, which is probability and measurement. How can we know this stuff? How can we put a measure on our uncertainty on all these things? Because that's the real key question, as we'll see. Now, it turns out the reason that we think about all these different kinds of universes, we have to first define universe. The universe, as I define it, is everything there is, materially and energy, that can communicate with this universe, which is sort of self-referential, but the point of it is we can only see so far into the universe. Our capabilities are limited by our instruments and our intelligence and also by facts of the universe itself. But just because we can only see so far doesn't mean that there isn't something quite right beyond what we could see. And if that stuff can communicate with what we can see, that is the universe itself. And the point of making this very important distinction is because physicists imagine universes which exist but which cannot communicate, cannot exchange information with our universe. We are completely cut off, they say, from these other universes. And so the only way that we can know that they might exist is not through measurement, which is impossible. Literally impossible. Not just that we're not clever enough, but it is impossible in fact, is because through the mathematics. Now, we're going to get into this in a little bit. We're going to talk about reification. The reason that the physicists want to imagine various universes is because of certain problems in quantum mechanics. The first problem about universes is, why is there something rather than nothing? Why does the universe even exist? How can it have come about? Well, we've all heard of the Big Bang, and some of us have heard of the theory called inflation, which produced out of nothing this incredibly vast universe we see about us. Well, how did that happen? Science has no real answer, no definitive answer, and at least no measurable answer, and this is unsatisfying. And so they seek in the mathematics ideas to solve this problem. There are ways to solve it that are extra-physical, metaphysical, which is to say philosophical answers that we could come to, and we'll discuss those. And the other reasons are, for various universes, problems and other problems in quantum mechanics of the very small, not just these very large universe creation events, but the very small. Why does a quantum mechanical wave function, so-called, collapse to a certain value? Scientists have no answer for this, and it doesn't seem that there can be an answer. In fact, from what we know, it seems the answers to us are forever going to be a mystery, and this is also deeply unsatisfying. So ways around this mathematically, metaphysically, have also been sought. So let's talk about the 4 types of multiverses there are. So if this universe was created out of the vacuum energy, we say, through inflation. Now, I'm not going to have any time whatsoever to explain these theories, but the idea is this vacuum exists in which there is nothing but a form of energy and a possibility of matter and energy to take shape. This explodes into being in this so-called Big Bang via inflation and creates the universe. That's at least the theory for our universe, the one we are living in now, and in which you're listening to this scintillating broadcast. But this vacuum energy, through a process called eternal inflation, may create other universes. At least the mathematics, some mathematics, not everybody agrees on all these mathematics, produces other universe, which sort of shoot off in different directions and which become untouchable by us. Now, there's 4 of them, as I said. One of which, the simplest which, of other multiverses are, every single one of them has the same physical laws that we have, but they start with different initial conditions, so the mathematics suggests itself. The second is, each of these universes has different laws. Not every single one is gravity attractive, for instance. Not every single one has the same constants, like Planck's constant, the speed of light and so forth. These shift, these vary. And they also have different initial conditions. Of course, the first type is subsumed by the second, because even if we could measure these other universes, there's no sample size that would tell us in any limited sense whether or not we're in the first or the second type of universe. There's just no way to measure these things, so there's no way to know which of these is correct. The third type is something called many worlds. Now, this is tricky. So every time an observation, or rather an interaction of a quantum mechanical wave is done, that wave collapses to a certain point. That's speaking very metaphorically. And those who have any quantum mechanical training will understand what I mean. But the point of it is, these things exist as waves of potentiality, which, when interacted with, are forced to take a value. Which value do they take? Well, they take a certain value that we measure. But why this one and not another one? The idea is, in the many worlds, is that they don't just choose the one we see, they choose all. At every single instant, every Planck second, a infinite number of universes are spawned from our universe by quantum mechanical wave objects taking every possible value, creating a new universe in which every possible value is present. And these are spawned off faster than you can faster than you can speak, faster than you can think. And it's a solution, all right, but it's a sort of partial solution. It does not account for why we continue to exist as we do, and it doesn't say how these universes are brought about. It would seem to require infinite energy, because at any one time, it's not only one wave function collapsing, it's many, and there's no sense of how any of these things are peeling off. And if they are peeling off, where are they? It's a very difficult thing to understand, and most people don't believe it. At least a lot of people don't believe it. Now, there's a fourth kind, and this is something we have to listen to. A cosmologist, physicist named Max Tegmark. Here is an edited portion of an interview. This is where we're going to get into the idea of reification. Here's his idea.
Level 4. This is where you've put your stake in the ground.
So this is the most controversial kind, where I am one of the very few proponents of it. And if indeed our universe is completely mathematical, then what you can do is you can, in principle, write a computer program which just churns out the list of all mathematical structures. And what we have to remember about mathematical structures is that they cannot be created because they don't exist in some kind of space and time. Rather, space and time exists within some of them. The mathematical structure of Minkowski space, which Einstein used for his space-time, it has space and time in it, you know. So they all just exist. And if there are other ones that can also support life and intelligent, self-aware observers who talk about things and think, they're going to feel just as real in theirs as we feel in ours.
So what does that literally mean in terms of all consistent mathematical structures would be realized, actualized in some kind of reality? Now, what would it mean to have another kind?
It's proven very difficult to make mathematical structures fully consistent, and mathematicians sometimes publish papers just to prove that something is consistent. But it means that if, for example, string theory turns out to actually be a consistent mathematical structure and yet not describe this world, then string theorists are still correct in the sense that it really describes a different universe at level 4. It's just not the one we happen to inhabit.
Well, Tegmark's idea is this, if I could boil it down even simpler. If we can write a set of equations down, those set of equations actually exist and actually, therefore, create a universe. It's not that our writing them down produces this universe, but any set of consistent mathematical formula that do exist imply the existence of a fourth type of multiverse. Well, this is the deadly sin of reification. Mathematicians write down formulas all the time. Statisticians do too, probabilists. Because a formula is written down is no proof whatsoever that the symbols mean what we say they mean. It just doesn't work that way. We've got the whole thing backwards. Originally, when we started doing physics, the idea was to simplify what we did see using mathematical equations. And using these simplifications to make predictions and to help us understand how things worked. We took the universe as it was, the measurable parts, the immeasurable parts we could say nothing about with the mathematics for the obvious reason. And these seem to fade away into the distance because they're not measurable. And somehow the idea was, from this very fine idea of using math to understand, where the math itself became the most important part. And the math itself was said to exist. Now, this is what Tegmark gets right about that. And if you listen to the interview further or read some of his writings, he is quite right that the mathematics cannot be created or destroyed in the sense that physical matter can, that these equations exist outside of a material realm. All of that is absolutely true. These universals are absolutely right. And in this, he's correct. What he misses is why these are the case. And I'll have something to say about it at the end of this broadcast. But in thinking about these things, we need to think about these multiverses. We have all these different candidates for multiverses. And how many of them exist? Well, an infinite number. Infinity is huge. It's bigger than you think. And in fact, there are bigger infinities than you could think. So that if everything were entirely material, and this is not what Tegmark is saying per se about his fourth type of thing, because he acknowledges mathematics are not material objects. But everything and the other types of multiverses are said to be material, or made of material plus energy. If that were true, and if there were an infinite number of things, there would be an infinite number of you. There would be an infinite number of copies of you doing exactly the same thing as you do, precisely exactly the same thing. The history of the Earth, the entire universe as we see it from the Big Bang, would have repeated an infinite number of times already. Precise copies with no deviation whatsoever. This is what infinity is big, folks. And not only that, there would be every subtle variation that you can imagine of yourself, copies of yourself doing slightly different things, and infinite copies of those. And not only infinite copies of those, infinite copies of completely different types of universes. Infinity is big, so let's count these infinities. It turns out you can count them, and that's the interesting thing. So there's the simple infinity everybody knows, where you start with 1, and then move to 2, and 3, and so forth up the ladder, until you reach a number which some mathematicians do call a number, and others don't. I think that the evidence that it is a number is fairly solid. However, it's a simple kind of infinity because you could list everything. You could just count everything up. 1, 2, 3, 4, 5. That's one type of infinity. That's the type of infinity that these multiverses appear to take in a naive understanding of them. But there's other types of infinities. That's the simplest. That's the smallest. That's a dinky type of infinity. But that's a huge infinity. That's an infinity already so large that it boggles the mind, as I'm going to prove to you in a few minutes. But there's another type. So imagine we have the fractions 1/2 and 1/3. Well, how many numbers are there between 1/2 and 1/3? We could think of these as sort of points on a line. We could pour other numbers in to fill that gap. Well, we'd have 1/4 and 1/3. We'd have a slightly smaller gap. And we could pour more numbers in to fill that gap. And we have a 1/5 and a 1/4. And we could pour more numbers into that gap. And we could continue this process ad infinitum, because using the countable infinity that we know, and we'll always have two sets of numbers into which it's possible to pour an infinite number of other numbers. Now, this is only a metaphor, of course, because I can't use equations on the radio and there are no pictures. But the point is, take any 2 points you like, and there'll be points. They'll be separate. There'll be a distance between them. Any 2 points, as close as you like, without touching. And into that gap, we could pour other numbers. And this type of infinity, where all of these gaps are filled in, is called the continuum, or an uncountable infinity. This is the next level, the next set. The cardinality of this infinity is larger than the counting infinity that we first talked about. Now, it's unclear what infinities we're using when we're talking about infinities. This becomes a very difficult point to follow. Which is the multiverses? Are the multiverses countable infinities, or are they a continuum? The infinity, counting infinity, is already impossible to imagine physical existence of things. And a uncountable infinity is also somewhat difficult to imagine. But uncountable infinities do not exhaust this type of infinities. We can have even larger infinities. Now, we've already crammed every possible space between any 2 points with numbers. But those numbers themselves we can think of as creations. They're not points. They're something even more vaporous than points. And into these gaps between these numbers, we can pour even more numbers. And we can, thinking about this, this all derives from set theory, but in between those gaps, we can pour even more numbers. And we can continue this process on and on, building up this hierarchy of infinities. Mathematicians typically work only with the countable and the uncountable, the continuum. But these other types, which appear in logic and set theory, are also types of infinity. They're vastly larger than these two almost negligible sized infinities. And these infinities, are they the physically real ones we're talking about? So this is the point we're going to get to next. But before this, we continue this metaphor of pouring numbers in any possible gaps, even these vaporous, ghostly gaps between numbers that we have. And we build these up. Eventually, we reach a point called omega. That's the name of it. That's the name it's given, capital Omega, the last letter in the Greek alphabet, which is a number so large that it's defined. The definition is defined that it's inconceivable. You cannot think of it. You could describe the process by which you get to it, but the number itself is defined so large that it's absolutely inconceivable. There's no possible infinity larger than this. And the interesting thing about this omega point is it's got very strange relations to what is called in philosophy the ontological argument for the existence of God. That argument says God is a being than which no greater can be imagined. So God is a being which no greater being can be imagined. And this is something like the omega too. The omega number, the omega infinity, is a number which no number can be larger than. So we're in this really tricky thing because mathematicians have built up this system of countable infinities and uncountable infinities, and that really exhausts the countable infinities, exhausts sort of number theory, the uncountable, what's called analysis and measure theory in our field of probability. But what about all these other infinities? They don't seem to fall into the physical world, and that's a sort of glaring hole. But before that, let's think about these infinities and the implications of these infinities. We've already seen some of the implications. And sort of we become incredulous. Are there really many worlds at every instant, every plank tick of the clock, which is shocking that all these universes are somehow peeled off? Maybe that's true. But we are incredulous. But then again, you can't use incredulity as an argument against something. That's a fallacy. So we have to think harder about these things. So everybody has heard of Zeno. I'm going to have two paradoxes for us here. The first one everybody has probably heard of. If we want to get from here to there, we have to first go halfway. And once we're halfway, we still have half the distance to go. Well, we could go halfway again, and there's still a quarter of the distance to go. And we can go halfway again, and there's an eighth of the distance, and we can go halfway again, and the 16th, and so on, ad infinitum. And it looks like we could never get there. And it seems if these distances are real, are actual, and not just potentially there, they're actually real physical distances that we must traverse, it would require an infinite amount of energy to move anything that has mass from here to there. Now, that's a paradox. Something has gone wrong in our thinking because obviously we do move. Things do change. So what's the solution to this? Well, if the universe were discrete and finite, like quantum, this is all quantum mechanics means discrete motion. Unfortunately, the word quantum mechanics sounds so new agey, so that's a problem. Well, if the universe were discrete, we could go halfway. We just count off the number of steps. And then we could go halfway again. There's just a certain number of finite steps, and so on. We can reach our destination. So if the universe is finite and discrete, this paradox of Zeno's disappears. But there's another one called the arrow paradox, or the Fletcher's paradox. So if you're shooting an arrow and space was made of points, if you look at any time the arrow is flying to its target, all of the arrow itself is residing on points in space. And it has to then, to move, shift to the next set of points. And so, but if we look at the arrow at any point in its flight, it appears that it stopped at these points. And then it has to magically disappear and reappear at the next set of points down the line. And this Zeno used to demonstrate that either the arrow is not moving or space is not made of points. But on the other hand, this is what happens in quantum mechanics too. Particles pop in and out of existence at specific points. So perhaps physically, the universe is a discrete thing, and this problem is solved in different manners. So this paradox of Zeno's of infinity doesn't seem to be as much of a problem. Now, the reason for all of this, the reason is this: we need to think about, well, probability and measurement. Now, we could measure things, and we want to understand things. And so we want to understand how infinity plays in our measurement of things. And probability has measures that could measure either countable infinities or the uncountable continuum type infinities. Nobody knows, as far as I can read, or at least very few people, understands how these higher level infinities beyond the continuum play in probability. But no matter what, our measurement, our ability to measure things is always discrete and finite. And probability is always a measure of our understanding, of our epistemology, not of what exists, but of what we can know of what exists. And think about this. Even if the number of steps between here and there is infinite and continuously infinite, or some higher kind of infinity, no matter what measurement we have, it will always be discrete and finite. No device will ever be able to measure with infinite precision an infinite number of points. And that means we'll always have gaps. And we'll never be able to prove what is in those gaps by measurement. And so probability will always be left when dealing with the contingent with some uncertainty. And so finally we reach the point where, because we can't measure these things, we need to ask ourselves, do they really exist? And the answer may be no. It could be that all this mathematics of multiverses and infinities and so forth are only really measuring potentialities. Potentialities are a form of existence. You are sitting listening to this podcast, but you are potentially out in your garden weeding. So this potentiality of you existing somewhere else exists in this sense. But because you are potentially out there does not mean you are actually out there. And the same thing is probably true with all of these multiverses and so forth. They're only measuring what could be. Now, this all ties back into, not only the ontological argument ties back into the omega point, but this all ties back into the idea of middle knowledge. So we have an explanation, a theological explanation of how the universe was created in the Big Bang. God created it, we say. And God's essence is his being. And he starts with the knowledge of all possible universes. This is part of his essence. But then he has a sort of middle knowledge of what you and all possible creations would look like under any potential circumstance. So God knows all the possible types of universes, and he could set them all running. And once he sets them running, if you like, this is a very crude metaphor, he knows every possible twist and turn that can happen. So all of these potentialities are up in God's head. And this is sort of the solution to infinities. It's the solution to all these multiverses. They don't actually have to exist, or they might. It doesn't really matter to us because Tegmark's right about the last thing. Our intellects and mathematics are not material, so we're continuing on in this universe no matter what, if there are other universes or not. And it's also the solution to our measuring and understanding uncertainty of whether these universes exist, or what we can do when we are confronted by infinities in the continuum and higher sort of infinities, which nobody knows how to handle at this point. There's much more to say on this, and there's no way I've exhausted the subject here. But let me give Carl Sagan the last word. I sat in a class with Carl Sagan when I was at Cornell, too, and he was a very good teacher. I mean, he had some strange views about nuclear winter and so forth, but the man had lots of nice things to say, and he was an excellent teacher. So we'll give him the last word from the very last episode of Cosmos. Stick around next week. It'll be another fascinating topic on the WMBriggs show.
We speak for Earth. Our obligation to survive and flourish is owed not just to ourselves, but also to that cosmos, ancient and vast, from which we spring.